Welcome to the Digital Republic, my podcast about science, politics, language, culture, and everything I find really interesting and important in the world. My name is Erik Schramma, but if you have trouble pronouncing that, you can just call me Eric S. If you want to know who I am, I'm a writer, translator, copywriter, self-declared amateur politician, and also currently doing my master's at the VUB in Brussels. Now, as a VUB student, I have been asked to interview a doctoral or postdoc researcher at the university in order to explain his or her research in a way that is still both accessible and understandable to a wider audience, which isn't always easy, I have to admit, with subjects that are as complex and sometimes strangely exotic as the ones we'll be discussing. Nevertheless, I think, I hope, I suspect, and I believe that we've succeeded in presenting the investigations these researchers are conducting into the mysteries of cosmic radiation, the political education of Flemish youth, the political dangers of the current crisis we're all struggling through, and even how to use the moon as a giant dragnet for exotic particles, and much more, in a way which is clear and not too difficult to understand, even though I have to admit that this was really an impossible challenge to get done in the space of just a single hour, but oh well. Nevertheless, I think, I hope, I suspect and believe that we've succeeded in presenting the investigations these researchers are conducting into the mysteries of cosmic radiation, the political education of Flemish youth, the political dangers of the current crisis we're all struggling through, and even how to use the moon as a giant drag net for exotic particles, and much more, in a way which is clear and not too difficult to understand. Even though I also have to admit that this was really an impossible challenge to get done in the space of just a single hour. But oh well. At the end, I believe we've ended up with what are some very interesting interviews, however, that give us a deeper insight into the research done by some of the VUB's researchers, as well as what drives these people to unravel the mysteries of the universe and the human mind, as well as why they've chosen to study at the VUB to begin with. Today, I will be speaking with Godwin Krampah, a PhD researcher and member of the Department of Astronomy and Astrophysics, where he works tirelessly to discover the ultimate origins of cosmic rays, and is also part of the worldwide hunt for exotic particles, which, for those who are wondering, are theoretical particles that physical scientists have long since predicted should exist, but no one has managed to actually find yet in actual physical fact. We also talk about how you go about trying to catch a neutrino by using the moon as a giant dragnet. We cover some of the international projects currently underway, of which the VUB is a more or less active part, which includes Project Ice Cube on the South Pole, and we of course also talk about his personal experiences as an international student in Brussels and the road he has travelled as a Ghanaian scientist living in Europe, as well as what's in store for the future. It promises to be an interesting, enlightening, and perhaps sometimes slightly confusing conversation, but don't let that stop you. In fact, let's get started.
Okay, so just as an introduction, my name is Godwin Krampah. And then I'm originally from Ghana.
Ghana, yes, I guess.
Yeah, so I studied my bachelor in Ghana at the University of Ghana. And then from there, I went to Radboud University in Nijmegen.
Oh, okay.
Yeah. Where I did my master's for 2 years in astronomy.
Okay.
And then soon after completion, as soon as I handed my thesis, I started my PhD here in the VUB.
Okay.
So yeah. So for my master's, I was in the astronomy department, the astrophysics department. But my research was mostly focused on cosmic ray physics.
Okay.
So this is a branch of astrophysics so it's a new branch. It's called astroparticle physics. So basically we are on the threshold of particle physics and then astrophysics. So yeah, which makes it kind of very exciting field because you benefit from both fields.
Okay. So it's indeed basically halfway between astrophysics and
Astrophysics.
ordinary physics, basically.
Yeah, exactly.
It's where the two fields meet.
Exactly.
Okay, and can you, because this is supposed to be like understandable for people who have no idea about physics, right?
Yeah.
And astrophysics, can you elaborate on what astroparticle physics and cosmic ray physics entails?
Yeah. So in the cosmic ray physics, which happens to be on the intersection between particle physics and then astrophysics. So astrophysics has to do with studying phenomenon on large scales, like about the universe and stars and stuff like that. And then particle physics most of the time focus on more like a microscopic nature. So things at the quantum levels and stuff like that, more like particle. So in the astrophysics, we try to bridge the gap between the two because cosmic rays are believed to be sourced or coming from some exotic phenomenon or some how do I put it? Phenomenon in the universe. Mm-hmm. So coming from a star or some black hole. So this is where the astrophysics is coming on. And then since these are particles, and so and then this also have really high energies and stuff. So we try to understand the physics of astronomy and then the physics of particle physics. So we bridge that gap between the two fields. So basically, so this whole research started about over 100 years ago when physicists found out that at any point in time, we are being radiated by particles. And by particles, I'm talking about ordinary particles like protons, aluminum, and nitrogen. And these particles are coming from somewhere in the universe. And these particles are very energetic. So scientists over the years in the last century have been trying to find out where these particles are coming from. What are they made of? And since these particles have so much energy, we want to know how did they become so energetic? And by talking about energies, I'm talking about 10 to the power 20 electron volt. 10 to the power 20. I don't know if this
people don't know maths.
Yeah, if this number makes sense to you, yeah, 10 to the power 20. Just think about that. So
which is a 10 with a little 20 on
20
top.
On top, exactly.
Like lots, 20 zeros basically. Yes.
Yeah, so many zeros. So, and then even more. So from our theoretical studies, we believe that there are other our theories from the early universe. A lot of phenomena or transitions happen that produce even particles even more energetic than that, 10 to the power 25. And so this is in physics, what we do is that we build theories, and then to see if the theory is valid or not, we confront the theories with experiment or observation in the case of astronomy. So we run observations, and then we see if our observations agree with our theories. And then if we have many observations agreeing with the theory, then this is a valid theory. So this is what we are doing. So there are theories that postulate that there are also other mechanisms and in nature that produce these exotic particles, these very energetic particles. So we want to probe these theories and also to understand where these particles have coming from. How did they become so energetic? How did they achieve such much energy? We want to know what they are made of. So now I'm telling you they are made of aluminum and proton and helium and stuff like that because we have measured, we have made observation, we have studied them. And so in VUB, in the cosmic ray department, we are basically focused on probing the nature of these cosmic rays, and also to understand their origin, and then also to constrain the underlying mechanisms that accelerate them to such high energies. So this is what we are doing in VUB. So VUB has a huge group that is actually looking into, which is more into cosmic rays and neutrinos. So the challenge with detecting cosmic rays is that at very high energies, like 10 to the power 20 eV energies, the amount of cosmic rays that are reaching is small. I mean, the flux is so small. And so to improve your chances of detecting such high energy particles, you need to build very large detectors, right? So if something is small, if you want to increase your probability, you build a very large detector to be able to hunt or detect them. But at lower energy, like 10 to the power 12 eV, 10 to the power 15 eV, the flux is abundant. There's a lot of these particles. So you can just build a small satellite or a small detector and send it to space, and then this can detect these low energy ones. But so there are currently experiments like AMS or other experiments that are on the International Space Station, like AMS, that are actually looking at these low energy cosmic rays. But
the EMS.
EMS, yeah.
Yeah. So that's is that a project which is also run by the VUB? I mean, partially.
No. It's just an
example. It's just that
the
data is also shared with the VUB.
Yeah, no, VUB is not directly. I don't know anyone who is directly affiliated with this project. But I mean, since we are in the same field, we have friends in. I mean,
you still get the data.
You still get information
because you know people who. Right.
So AMS is actually, it just stands for Alpha Magnetic Spectrometer. So basically, they are focused on the low energy cosmic rays, and so they have a satellite on the ISS, the International Space Station, where they are looking for cosmic rays coming from the universe. And so so basically, this research is also trying to answer what the cosmic ray components are or the compositions are, whether it's made of aluminium and what fraction, in what fraction, how much percentage of aluminium is in your cosmic ray composition, how much proton is there, how much helium is there, how much nitrogen is there. So they do this kind of studies. But at the VUB, we are more focused on the higher energy cosmic rays.
Right.
And this,
which are harder to find. Basically.
Yeah, which are harder to find. So, and since they are harder to find, so like I mentioned, because of so there are two ways of detecting cosmic rays. We have a direct measurement, which the AMS is doing. So they put a satellite in space, right? And so the cosmic rays directly interact with their detector. So the cosmic ray, they are detecting their cosmic ray directly. But on Earth, right, you have an atmosphere. We have an atmosphere. When you think of an atmosphere, it's just a layer of gas with particles in it. So when cosmic rays come from wherever in the universe, they have to go through our atmosphere to get to us, right? So in that case, they don't come directly. They have to go through the atmosphere. They interact with other particles in the atmosphere, and so we don't detect them directly, but we detect them indirectly. Okay, so you think of it that, so there's a particle in the atmosphere, the cosmic rays come and then hit the particle, and then the particle breaks down, and then it produces a shower of particles in the atmosphere. And this shower of the atmosphere falls like a rain onto the ground. So if you have a particle detector on the floor, this shower of particles comes down, they collide with each other, and then they produce a huge avalanche of particles that fall on your detector. And by measuring this avalanche of particles, you can infer how much energy it has. We can also make a composition study to see the nature of, whether it's aluminium or what its mass is of the initial or the primary particle, what started the interaction. So at the VUB, we are not, in my group, we are more focused on making this indirect measurement. But instead of using the particle information, the particle that develop in the atmosphere, we are not doing that. We are actually looking at the emission that is being produced by these particles traveling through the atmosphere. So now the idea is, if you have a particle that is, propagating through a medium, right, at a very high speed, it produces radiations as it propagates through a medium. And this radiation is what we call the Cherenkov radiation, or the Cherenkov effect, So we are more focused on looking at the radio emission that is being produced by these particles that are going through the atmosphere. And then we have our radio antennas in in the Netherlands. So we have our observatory in the Netherlands. We use the LOFA observatory, the low frequency array observatory in the Netherlands. It's in Drendelo. So basically, these radio antennas are looking into the whole atmosphere, into the whole space. And so when this radio emission that is produced by each of these particles, they look at this radio emission, and by looking at the intensity of the emission and studying the radio profile, we can actually tell what we can infer information about the initial particle that start the reaction, the interaction there. So we can reconstruct the energy of the particle. We can actually tell about the composition of the particle and stuff like this. So this is the broader thing my research group is doing. So let's bring it to my work, what I am doing in this research group. So now, another question with this cosmic ray physics is to know where these particles are coming from. Now we look at their composition measurement, what they are made of. The next question is what we also want to know is where are they coming from? So, but cosmic rays, as you know, these are particles, right? And they are coming from somewhere in the universe. But because cosmic rays have mass, and together with the Earth's magnetic field, right? So it's charged. They have these particles, they have mass, they have charges. So these are protons, helium, which are charged. Mm-hmm. And because of the magnetic field of the Earth, they are being deflected. So it's probably coming from that direction, but because of the magnetic field, they are being deflected. So you see them coming from that direction, which doesn't point to the source. So so this makes it a very challenging thing to probe the origin of these particles. But at very high energies, right, then they can be able to, the effect of the magnetic field is less on these particles. So very high energy. This is why we are focusing on very high energy particles, to be able to constrain
basically the faster they go, the straighter they go.
They go straight, exactly. So the faster they go in a straight line. And then, so if you see you can able to tell, if you reconstruct the direction and it's coming from that direction, you just focus there and see what stars or what sources are up there. So if it's coming from that direction, you look up there and see, oh, there's a black hole there. So, it's probably coming from a black hole. Oh, there's this supernovae. So it's probably coming from that supernovae. Or, I mean, I'm sure you're getting the idea. Or there's this star, or there's some sun, or from the sun, or something, you know. So, so we are more focused on the very energetic ones to be able to probe the origin of these particles. Now, another way we can also probe there. So in my work, I am also trying to, another way we can also find where these cosmic rays are coming from is not to focus on cosmic rays, but focus on neutrinos. Because neutrinos, as you know, are also particles, just like cosmic rays, but they do not have charges, and they do not have...
Hence the word neutrino is in neutral, right?
Yeah, neutral. So they do not have charges, which means that they are not affected by the Earth's magnetic field or the magnetic field of the galaxy, right?
Yeah.
So which means that when you're able to measure the direction of the neutrino, it points directly to where they are coming from. And neutrinos are produced in the same, have the same sources as cosmic rays. So by looking at the neutrinos, the sources of the neutrinos, you can also indirectly gives you the information about the cosmic rays, because cosmic rays and neutrinos are produced around the same sources. So in my work, instead of looking at cosmic rays, I'm looking at neutrinos, which we believe are produced, we are looking at neutrinos. Now, but because neutrinos are very small, they have low cross-section, which makes them very difficult to detect. And this is another challenge. So you need to build very big detectors with very high depth so that the neutrino can travel. When it travels through, it takes a lot of time for it to interact at some point. So that
because you basically have to throw a big net.
Yeah.
Because they have small fish, big nets, basically.
Exactly. So this is a challenge. So you need to build a detector the size of the Netherlands. Or I don't know. So now there are experiments in the Antarctica, the South Pole, called the ice cube, which are measuring neutrinos. What are that produce? I mean, neutrinos coming from somewhere in the universe. There are also experiments like Ariana or ARA. I mean, I don't know if these things make sense to you, but I'm just mentioning this experiment for, I mean, whoever watches this can actually just look at this experiment. ARA or Ariana or Ice Cube, they are all looking at for neutrinos in the ice in the South Pole. So in my work, I'm using the moon because, I mean, so the moon, as we all know, is just a huge piece of rock that is hanging up in space, and all the centuries people are just writing beautiful poems and stuff about the moon, you know. So it's about time we begin
the moon, to be honest, but it is a big rock, yes.
Yeah. So it's about time we begin to do some interesting science with the moon. So we thought that, okay, if we could, so if, because the neutrino the moon is hanging up there, it's a huge, has a very large surface area. So there's a chance that neutrinos hitting it can interact in it, and so when the neutrinos hit the moon, they interact with other particles within the moon, and then they produce a shower. So it starts an avalanche of interaction. So it has energy, it comes in, it impacts something, so it splits up a particle within the moon, and then the other particles gain enough energy, they also interact with other particles, then you have this shower, a cascade developing in the moon. And when you have this cascade developing in the moon and traveling in the moon, they have something we call the Ascarian effect, which is when you have charged particles that are moving at speeds higher than the speed of light in that medium or in the moon, they produce emission. And this emission is in the radio frequency band. So what happens is that when neutrinos hit the moon, right, and then you have particles that are being produced in the moon, they travel faster than the phase velocity of light in the moon, they produce this Ascarian emission. Now, this emission comes out of the moon. So they are produced in the moon, and the emission propagates out of the moon and comes outside the moon. So what we are doing is that we are at LOFA. So LOFA in the Netherlands, this is the observatory we are using. And then we are pointing our radio antennas at the surface of the moon. Now, if the radiation comes out of the surface of the moon, we are able to record, to be able to pick up the signals that come out from the surface of the moon. And from this, from the intensity of the radiation, we are able to, so in this preliminary stage, we are just looking from the intensity of the radiation, we could tell the energy of the neutrinos. And so this experiment has there has been previous experiment that has been done using the moon as a neutrino detector or cosmic ray detector, but all these experiments has not yielded any we haven't observed any results yet. It's all now results, right? So but unlike what I am doing now, all these previous experiments have looked for cosmic neutrinos or cosmic rays from the moon at very high frequency. And at very high frequency, I'm talking about over 1 gigahertz frequency band, above a gigahertz frequency band. But what we are doing is that we are looking at this at a lower frequency of 150 megahertz, which is, very small frequency. And I don't know how to explain the technical details to your audience, but at very high frequencies that these guys were observing, you are just sensitive to cosmic rays that hit the rim of the moon, like the outer edges of the moon. You are just sensitive to that if you are measuring the whole frequency, which means that your probability is also small, right? Because then you are focused on just that area around the rim of the moon. If you think of the moon as a circle, just the rim, the circumference, just focus on that. Yeah. But the advantage of going to low frequency is that at low frequency, you are sensitive to the whole lunar surface, the whole moon. So which increase your detection probability. So now you are just not focused on the circumference, but you're focused on the whole area, right? So with our observation, we stand a higher chance of detection. So this is what we are doing now. I'm just starting my second year of the PhD, so this is a work in progress. Really hope to come up with something. And if we're able to make this observation, I think this will be novel. And VUB should be in the spotlight,
Yeah, well.
Yeah. This idea of using the moon as a detector has already been there since in the 60s. It was just a theory, but there hasn't been any experimental observation. So, and this, if we're able to make this observation, this will be the first time something like this has been observed. So this will be, yeah.
That would be quite a coup, yes.
Yeah, it would be cool. Yeah, I mean.
Well, that's yeah. All right. So, and anyway, I bet also, if in the meantime, also quickly read up on iceberg, on the iceberg neutrino observatory, which is indeed
Ice Cube.
Yeah. Which is indeed on the South Pole.
Yeah.
It's only been built in 2009, so not really that long yet.
Not long ago, yeah.
No.
There is a big group at the VUB, in case you are not aware. There is a big group on Ice Cube in the VUB, in the particle physics department.
So they're basically they're a pretty big part of this of this project.
Yeah.
Which is, by the way, also an international project. Like,
yeah, it's an international project, but VUB has a strong partner.
Yeah.
So that's a big group. Yeah.
Many of these projects in physics and space exploration tend to be international, of course, because
of course, I mean, you can pay for it.
Investment.
You can pay for it, yeah.
Yeah, because when you have to fork over millions and sometimes billions of euros or dollars, then yeah, you basically need to spread the costs, eh?
Yeah.
So it was pretty interesting, and indeed. And you talked, so basically those neutrinos, it says here that indeed those neutrinos are in Ice Cube, the way they measure them, like basically the way they know that they, because of the Cherenkov radiation, which shows up, which for people who, because when you say Cherenkov radiation, most people don't really know what the hell that is, but if you think about let's say a movie and you're talking about a scene where there's a nuclear reactor.
Exactly.
Blue glow.
You see this blue, that's the Cherenkov
blue
radiation.
glow, that's the Cherenkov radiation. And if you see that, you're probably going to die. Pretty much.
yeah. That's. I mean, when I think of Cherenkov radiation, this is what comes to my mind when you go to the nuclear.
Chernobyl, basically, that's the color of, But because when you use the words, most people don't know what it means. But when you use like a nice filmic example, nobody knows that.
Yeah.
But that's so basically, essentially, what you are trying to do, it's sort of trying to connect the very large of the cosmic scale with the very tiny of particle physics, and trying to find out just. Where does stuff come from? And especially where do the exotic particles come from?
Yes.
And of course, the most difficult thing with the exotic particles is that they are exotic, which means that you don't see them a lot.
Yeah.
That's pretty much what it means, right? Yeah. But the interesting thing for me is, in fact, that when you talk about the exotic particles, these are things that a lot of physicists have predicted that they should exist.
Exactly.
Like a long time ago, they predicted that they should exist. And only now we're finally doing these experiments and seeing that, well, they do actually exist, or they don't exist, or they might exist. It's like, as well, with the dark matter, which is also a thing studied at VUB.
Yeah, there is there is some people in the astronomy department who are looking into this, but I don't know the full details of their participation or what kind of groups they are working with. I don't know much about this.
No, because I did my homework, so I read through the whole website and stuff, But which is also one of those examples of something which is predicted should be there, but nobody has actually observed it. So that's one of those one of the big questions. So it's all very very interesting, and
it's the same about the black hole, right?
Yeah, you can't see it, but it should be there.
It should be there, but for the first time, I think 2 years ago, we've been able to image the rim of the black hole. So this is not just an academic exercise or some theoretical artifact, but it exists, you know. So
it's actually about something which is out there. And now, of course, the question is, now we're moving on to the next question, which is what exactly is a black hole? Because I've also heard some people say that it's like as quantum singularities, which is basically gigantic hole in space, or it might just be a very dense planet. I've also heard that. Yeah.
So actually, let's talk about stellar evolution. So stars have been produced at some point in the history of the universe, and then stars grow, and by growing, I mean they gain more mass by accreting mass from other in their environment or from other stars in their neighborhood. They become dense, and then they evolve with time. So at some point, the star becomes so massive that, you know, what keeps a star in equilibrium, or what it is that you see in the skies, is a balance between the force of gravity and then the radiation pressure. So the mass is compressing. It's like you have this huge. So when you think of a star, just think of it as an accumulation of gas. It's just a dense piece of gas, like small particles dense together. And so this density is falling, right? Something needs to come out to keep that equilibrium, to keep it like a ball. So if you just think of a ball, a football, right? You have a gas that is pushing outside, and then you have the walls of the ball that goes in. So for the ball to be what it is, there has to be this balance between the gravity of and then the pressure outward.
Yeah.
So this is what keeps stars in equilibrium. Now, as stars evolve, they gain more mass, right? And then there is a lot of, and what produces this radiation in the core of the gas. So the more mass comes, and then the mass is so dense that the core becomes so hot. And then there's a lot of reactions in the core, like a fusion reaction taking place in the core. And this fusion reaction is what is producing this radiation pressure that is balancing the force of gravity, the self-gravity of the star. Now, at some point, the star evolved to the point that the gravity becomes so strong, and also the nuclear fall in the core of the star also get exhausted. So at some point, the star collapses. And at this point, the star collapses, and so this is what we call the final stages or the final evolution of the star. The star collapses into what we call a black hole, depending on the initial mass of the star when it collapses, or you can form a neutron star depending on also the mass of the star. So you can think of the black hole as the last stage of evolution of the star, which is just a huge dense of mass, like really dense, that anything that goes in gets pulled into it, you know. So I mean, for me, this is how I conceptualize it. I mean, this is what it is. And that's why people say, okay, when anything that goes in the black hole gets swallowed and all that stuff. But it's not like, it's not black, but it's because when light goes in, it gets swallowed. So you can't see it. That's why we are calling it black.
Because the gravity of a black hole
is so intense. Even light it bends around it. Yeah.
So it's not actually black, but it's practically invisible. You can't see
invisible. You can't see it because
it's truly invisible.
Yeah. And so 2 years ago, is it 1 year ago, when they actually imaged the black hole? Actually, my previous university in Nijmegen, they had an active role in this, and then the press conference was being given by one of my
all right.
Yeah, one of the professors in the department at the time. Yeah.
Yeah, so I remember that as well.
From Nijmegen.
Also for all the space news and stuff, you know. So
Yeah. So it was a really exciting time to be around and to see this discovery. So for me, that was.
So many interesting things to talk about. But where do you start? You know.
Yeah.
But how basically did you get into astrophysics? How old were you when you decided I want to be in astrophysics and go to astrophysics when I grew up?
Actually, I didn't actually think of going to astrophysics when I grew up. It actually just happened. So when I was in school, in high school, throughout school, before university, I was really good at math. I love math. And so I always wanted to do something with, like, say, engineering or probably do business, because my parents were business people and I was dealing with money and doing all these calculations every day in the shops and all this stuff. So I like numbers. And then when I got to the high school, in the final year of the high school, all my friends wanted to go to the medical school. All my friends. And so I was like, okay, and in my country, going to the medical school is like more prestigious than going to do math or to do physics or to do chemistry and stuff like that. So at some point, I also wanted to go and do medicine, and it just didn't happen. So at the university, I was like, okay. So in my university, you will get admitted into the university, and the first year we all do all kinds of courses. You can do biology, you can do chemistry, you can do psychology and all the stuff. So in the first year, I did many courses. I did computer science, I did math, I did physics, I did chemistry, I did psychology. No, not psychology. Sociology. I picked sociology. Yeah. So after the first year, then in the second year, we have to choose our specialization, what you want to do.
Yeah.
So there was a meeting from the physics department where they invited these people to come and talk to us about the prospects and what you can do as a physicist and all that stuff. So this is when, I got to, see, okay, physics is interesting, and I was also doing math at the time. So math was we're just doing this hardcore calculations and derivation and algebra. And it was so abstract to me, actually. So I saw physics and I saw, this is a way to apply my, see the beauty of math. I think it's through physics for me, at the time. So you do all this Fourier transform in the maths department. And then you do all these hardcore calculations, and then you come to physics, and then you have to actually use the idea to do something, like to do science or to do something,
So this was the practical application of math.
Exactly, to me. So this is how I got into physics, but not into astro. So my bachelor, most of the courses I did was more into material physics, or we call it condensed matter physics.
Mm-hmm.
So in my final year, I had 2 courses in particle physics and astrophysics in my final year. Just 2 courses for each. And then the professor told us about CERN and at the Large Hadron Collider and what people are doing there and all the stuff. And then I had astrophysics course, and then they were talking about stars and galaxies and all this stuff. And I'm like, this stuff is really exciting. So why don't I do this? So I immediately finished my my bachelor degree. I had 1 year. In my country, you had to work for the government for free for 1 year after you finish your studies. So in this 1 year, I was hired by my department to stay over and teach and do some teaching. So this 1 year, I was in the department doing some teaching and reflecting on what I should do. And I read a lot of stuff about astronomy, and then I began to apply abroad. So I applied everywhere in the world, like, okay. Even though I literally did not have enough physics background, so people call me for interviews, and I was just saying all kinds of, I think, gibberish at the time. Yeah. So eventually, I applied to Nijmegen too, and at the time I was not just looking for just admission. I was also looking for funding, because coming from Africa, you can imagine how expensive this is for us. So luckily in Nijmegen, they have this scholarship for 30 recipients every year. It's a special scholarship for the international student, the first 30 best applicant, like with the highest GP or whatever it is. So luckily I happened to be one of those 30, so I got a scholarship. So this is how I got to Nijmegen. And it was this was where I really developed this passion and things for astronomy, because then you are surrounded by people like real astronomers who are really passionate about what they are doing, and and you have colleagues who are also really passionate, and and then so it's just people, the kind of people for me, the kind of people I my association, the kind of people I met when I studied. I went to Nijmegen with, so I actually built my my strong desire and interest in astrophysics, actually.
All right then. But then you, at some point, you left Radboud, and then you came to VUB. So why VUB specifically?
So the research group I was working in, I was working also for my master's thesis. I also worked on radio detection of cosmic ray, right?
Yeah.
But over here, then I was working in an observatory in Argentina. So in a collaboration called OGE. So this, since they're also working on radio detection of cosmic rays, is so my current boss is also doing radio detection of cosmic rays, but with LOFA.
Right, yeah.
In the Netherlands. And then I was also doing the same thing, but with Argentina. But because my boss in Nijmegen had a close relation with my boss here, so it's like they were all collaborating, and he was part of this mini collaboration. So this was how I got linked up and got into this.
Basically, it helps who you know.
Yeah, I mean, this is how this things work. Yeah.
There's also, not a huge circle of of people who work in this field.
Sure, it's just a small group of people
throughout Europe. So it's quite easy to know all the people.
Everybody, exactly. And, you've probably seen them in a meeting or a conference or something, So
yeah. I'm sure that at some point in the future, I'll also see your face coming through space.
I hope so.
Especially when finally those particles hit when you hit one of those particles.
Oh yeah.
Because I know, I mean, as I said, I also try and follow up on this news myself.
Yeah.
Even though I'm not a physicist, and even though my math is frankly horrible. But I'm interested in this, so I do follow, and I know that this search for these particles is a big thing. It's a big thing
going on now,
and it's been going on. Yeah, it's like one of the main projects in the world basically right now.
Yeah.
And people are frustrated basically by the fact that they still haven't found anything, even though they've been. So if this thing hits, it's a big thing in physics basically.
Yeah.
So, yes, if you find this thing, your face will be on the internet.
Yeah.
All right then. Right, nice. One thing I also like to ask people, basically, who are your inspirations? Is there anyone who inspires you? One who serves as an example, for instance.
Yeah, for my career, or like.
Yeah, just in general. For your career, but also in general. Just name whoever is like the big, if you have one. Not everybody has one, of course.
Yeah.
Personal, but lots of people do. So if you have one.
Well, I think I have a lot of inspiration from so many people, and depending on the situation.
Yeah.
Right. So, So from like in my field, I mean, with my work, I mean, in what I do now.
Yes.
I think I get I get a lot of inspiration from so many people, actually. I mean, from friends and my colleagues and stuff, because I mean, it's just the passion with which we talk and do stuff. This is what keeps me going. Sometimes I'm down and questioning why I'm doing what I'm doing. And then you meet and you talk to another friend and he's so excited. Oh, have you heard this news? You found this black hole. Oh gosh, it's crazy. Then like this kind of people. So it's just not just one person, but it's just a group of friends and people,
Mm-hmm.
Yeah.
The entire field cross-pollinating constantly.
That is the idea. So it's like iron sharpening iron, like people telling, hey, I mean, like you meet people in the field and, just talking about this and having debates over drinks and, these are the things that keep you going, like inspires you, you have an argument and then you lost this argument and the next time you're like, okay, I'm going to do my research and then come back for this,
The university life, is.
Yeah.
A little bit. And, right. And then basically to follow up on that, but like slightly differently, so many scientists in all fields basically are inspired by specific books or authors.
Yeah.
What are your absolute favorite books or movies that you think everybody should read or everybody should have seen?
Well, I mean, apparently, my reading interests are really very diverse and very unrelated to my studies. I read all my books. Okay, maybe you can't see from here, but I have a bookshelf of books, and there's no science book in there. Every book there is about leadership or business. So, I mean, all this stems from my background. I come from a country with, I have seen a lot of problems, and I have been thinking about this over the years. And I realized that the main pitfall of most developing countries, okay, let me not generalize it, my country, which is Ghana, is that it's a leadership crisis.
Yeah.
So corruption, incompetence, stuff like this. So since then, I have begun to, invest myself, find out about what leadership is all about, and whether people are born leaders or you can learn to be a leader, or, and what I can do, in the future to help. And so these are the things. So these are the kind of books I read. So one of the books I'm reading now, and I think I recommend, is a book. Let me just take it and probably show it to you. Is this book? I'm not doing an advertisement, but it also says
with Why.
Why,
right?
By Simon Sinek. Where it actually addresses things like, if you do something, why is the rationale? Why am I doing what I'm doing? You gotta find this deeper, convincing reason for why you are doing it, or you're always gonna get it wrong. And so I think it's one of the books. I bought it not long ago. I think a week now, and it's a really nice book.
So it's basically rationale your way through life. In the scientific method, basically.
Yeah.
Why you're doing things.
Why exactly, and be critical. That's all I can say. Be critical. Just why am I doing this, and just thinking. And this it cuts across everything: science, work, career, everything. Real life, friendship, everything. Why are you doing what you're doing?
Yep. Then so you're a foreign student, not from Belgium.
Yeah.
You live in Brussels?
Yeah.
Or outside? Yeah, you live in Brussels?
Yeah.
Right, then of course, because it's nice and close to the VUB. The reason I study at the VUB is because I used to live in Brussels.
Brussels,
At the end of the tram line.
Yeah.
At the end, so basically I just meant to get on the tram and just go half, and 15 minutes later I'm at the VUB. But then about a year ago I moved to a village deep in Flanders, so I'm hours away. I didn't know I was going to do that.
Yeah.
It's a good choice, but it makes life harder when it comes to the VUB. But oh well, you gotta do what you gotta do, right?
Yeah.
So you live in Belgium, and you live in Brussels specifically.
Yeah.
You're an English speaker, obviously.
Yeah.
Have you managed to learn any French or Dutch by this time?
Well, languages is not one of my strongholds, so I went to the French class and I didn't finish. So. I don't know. Language is not my thing. I don't know. It's just so hard for me. Yeah, because my background, actually, I'm supposed to be speaking French too, but apparently I cannot, because I'm coming from a part of Ghana that is part of Togo. That used to be part of Togo, but so I have families on the other side of the border who are speaking French, so
right.
So I should be able to speak French, and I had exposure at a young age to speak French, but I just couldn't.
It never worked.
It never worked for me. Yeah, I just learned, and I studied English in school. I just need to write. I need to just pass my exams, you know. And this is what I did. I just bluffed my way through school in French, you know, like okay.
But you got French as well at school?
Yeah, throughout school, from primary school to
primary school. Okay.
Yeah, all the way to high school.
All right, then. Yeah, because of course, for those who don't know, that part of West Africa, it's
French,
English and French.
Yeah, mostly French actually.
Mostly French. Well, of course, there's Nigeria as well, which is English mostly. And
Nigeria, Ghana, Gambia, Liberia.
And all the other little countries there are like French, heavily French.
Yeah.
So I also got French at school, by the way, at high school.
Yeah.
And I was terrible at it. Absolutely terrible. And I basically bluffed my way through it as well. Funny thing, like 20 years later, I ended up living in Brussels. Right?
Same. I'm like, who knows? I mean, here I am in Brussels. I'm like, okay, I have to speak French. Irony of life.
Yeah, but luckily I'm like a language guy, right?
Yeah.
I mean, I even study languages, so I managed to pick it up quite easily, and my French now is like so much better compared to what they taught me at school. You know. But hey, that's where life takes you, eh? But I mean, how have you adjusted to like life in Belgium, in Brussels specifically? How do you find it? Is there like any frustrations there, or do you like go, yay, that's every day?
Yeah, I mean, okay, so I mean, living in the Netherlands and then coming here was a huge transition for me actually, even though they were just like proximity, like an hour or 2 hours from each other, you know, because in Holland I never have to think about learning Dutch. Never, not even once. I never even took a Dutch class. I was there for 2 years. Never. And then I got here after 2 months or 3 months. I'm like, no, I need to go for French class. And this is really frustrating. People are not, I mean, I would expect that, okay, this is the EU capital and, you know, like, okay, people should be speaking more English and more international language. But up to my surprise, this is not actually the case. Actually, this is not the case. You know, you go to places and you say English, you say no. And it's like, they don't even want to talk to you again. It's like, done, you know. So this is really hard and it's difficult to, I don't know, to live like this. I mean, because I don't feel like I belong to the society, and this is really, this is hard.
Yeah. Well, I mean, yeah, I understand it exactly because I lived in Brussels for about 10 years.
Yeah.
Before that, I came from the Netherlands as well.
Yeah.
So and for me as well, for us, it was also it was actually a big transition from because you think indeed when you look at the map, right? You've got the Netherlands, you've got Belgium, Brussels in the middle. Yeah. So it should be all sort of the same.
Same, yeah.
But it's not.
But it's different. Yeah,
even in Belgium itself, it's like you've got like 3 different little countries in one. Yeah. 4 if you also count the Germans at the east, you know. And you travel like 10 kilometers and you're in a completely different country, even though you're still in the same country.
Yeah.
But it's for us it was also a huge transition.
It's different actually.
Transition. And as well, the thing which you just said about it's the capital of Europe, right?
Yeah.
But yeah.
And this was also one thing I thought of when I accepted a job to come here. You know, like, hey, I'm gonna be in Brussels.
Capital of Europe should be fine.
Europe should be fine. I'm done. You know. Yeah.
No, it really isn't. No, I know, eh? Everybody has that. I can tell you that right now. Yeah. Everyone has that.
Yeah.
And also all the expats and you know recent immigrants to Brussels, especially I talk to.
Yeah.
Everybody has that.
Yeah, I think it's all my friends have the same problem. You know. And I don't know.
So you're not the only one, you know.
Yeah.
And there are like a million foreigners in Brussels anyway.
A lot. So
there's like a million people there who feel exactly like you and me.
Yeah.
But right. Anyway, so do you think? I mean, so what's for the future? Do you think that at some point you'd go back to Ghana as well?
Well,
perhaps to make your difference with your leadership.
I would love to if I'm given the opportunity, but it looks like if someone doesn't want a change or something, then you can force that change on the person, right? So it's complicated actually, because I mean, over the years, I've seen people who were so passionate about what they do, and they go back to change stuff, and after some years, they just get frustrated and they just leave, you know.
Yeah.
So I mean, it's a really complete. I mean, just think about his home. You know, it's like this is what you call home. Who would want to be home? You know, everybody would love to be in his home.
I mean, if you can't abandon it, but it's just frustrating when you go back and nothing changes.
And nothing changes, and you can't even do science, especially science. I mean, you literally cannot do science, because I heard the last time I checked, just 0.1% of our GDP, or I mean, is it GDP? Yeah, GDP. I mean, no, not GDP. What the government, right? I mean, of the annual government budget goes into education.
Right. Yeah. Basically, the
0.1%.
This the entire budget.
This for the whole education, not science. Whole education. So the sociologists are going to get from the same basket. The scientists are going to get, the business guys. It just tells you what kind of system we run. You know, it's just horrible.
That's pretty bad, actually.
Yeah, I know. I mean,
that's pretty bad.
Yeah, I mean, when you, especially in my field, I'm so not unlucky, but I'm in the sense that I'm coming from a very religious country, and I'm in this kind of studies. Mm-hmm. Nobody's gonna buy anything I'm gonna say.
Right? Okay. Yeah, like that.
When I talk about a big bang, they'll be like, "Come on, you're a lunatic." It's like.
Yeah, right. That's a whole different problem. At least we don't have that problem in your
exactly. You know,
and actually say that. Yeah, I think there was a big bang, not created by divine touch. But when you go back to Africa, that's a bit more difficult.
Nah, you can. Yeah.
And then of course there's always the politics.
Yeah, politics.
Yeah, I know. Because my wife, she's from South Africa.
Oh, okay.
So I know, that's like it's something you don't know in Europe. I mean, Europe is also like has its own problems. Am I right?
Yeah.
I know, and also it's got its own political shit going on, basically.
Yeah.
But Africa also has its own very specific leadership.
Yeah. I mean, it's one thing if people lead from the point of ignorance, and not from the point of knowledge. There's a problem.
Yeah.
If you have leaders who have a high school diploma and he's a member of parliament, I mean, just think about this. I mean, or someone who makes so much noise. I mean, these are the people.
Well, yeah, indeed. Again, South Africa, one big problem is people who run state companies, but who don't even have the high school diploma.
It's I don't know. I think it's across the whole Africa. It's like this. Just
it's. I mean, there are a few bright spots. I think, like Botswana, for instance.
Botswana seems to be good. Yeah. I also heard about Namibia or Mauritius. This country.
Mauritius also seems to be quite corrupt, though.
Really?
What I've heard, I mean, I might be wrong though. I'm not an expert on Mauritius, but I've heard that Mauritius also is quite corrupt, but Namibia seems to be doing quite well.
Quite well, yeah.
Also,
Seychelles Island. This one also Seychelles, yeah. It's also doing well.
But on the whole, indeed, it needs some work still.
Yeah.
Who knows? You never know. I also believe though that when it comes to these things, you never know.
Yeah,
things do change and things get better.
Yeah,
and also because when you look at the whole history of the African continent, colonization, decolonization wasn't so very long ago.
Yeah,
like in the 1960s, basically.
Yeah, in the 60s. Yeah.
It's less than 100 years ago.
Ghana was the first, and we had 57. So
indeed, so that wasn't that long ago if you think about it.
Yeah, but it's long ago for people to start thinking, like
I know. But I mean, the thing I try to see this in a sort of like positive way, because in Europe you see, all right, democracy and the democratic way of thinking and stuff that is more or less ingrained in people right now. It came after so much trouble and hundreds and thousands of years,
World War 1 and 2,
2 world wars, a cold war, communism, Nazis, French empires, British empires, all that shit. It took maybe 2,000 years to get here. So when you think about it, from 1945 to now, less than 100 years, there is some progress, actually.
No, but I mean, this whole time Europe was going through this transition, Africa existed, right? We also had our experiences, but haven't we learned from that? You know, we can, I mean, I think I've moved from this point of making excuses for Africa than just saying, hey, we got to take responsibility for whatever it is.
Of course, You know, of course. I mean, that's like you need to strike a balance when it comes to that between, you know, seeing what's happened before, and being realistic. Another one, having still your idealism and trying to strive for better.
Yeah.
No, but that's politics. Politics is just everywhere, you know.
Besides, with this current system or the world as it is now is different. I mean, with now this whole technology, we don't. I mean, there's access to information everywhere. You know. You can read about what countries and civilizations went through, and you learn from that. You don't have to experience that. You just have to learn from it.
The question is, how many people actually read things? Because it takes, I mean, that's like opening a book or even opening Wikipedia and reading these things. It takes like concentration. You need to concentrate.
I know, it's a lot.
And it's very much easier to just get your phone and start playing video games.
Yeah, that's true.
I mean, I always try to get my, I've got a son who's 12 now.
Yeah.
And I always try to get the guy off his phone.
Yeah.
Because, you know, barring him from playing video games and stuff, the problem is he needs it for his homework, for his school, because of Corona and stuff. He needs to like photos and send and stuff. But no. That's life in 21st century.
Yeah.
You have to make the best of it. So when do you think, by the way, you'll be, what's your plan? When do you think you'll get your PhD?
So ideally by my contract should end in the November of 2022.
2022. So two and a half more years.
Yeah.
Okay, and then it's step. It's this. It's what are you going to do after that? Basically, do you think?
Just if I want to be in academia. Then probably I have to do at least 1 or 2 postdoc before at least going back to Ghana or something. But if I don't find anything in academia, then probably I'll go more into data science or programming or something.
All right.
Yeah. Because I don't know. I mean, there's this question I saw in your questionnaire, like what does a day of an astronomer looks like? This is a very interesting question, and I think a lot of people I should say this so people can have a glimpse into what we do. So there's this stereotypical mindset of astronomers of sitting or peering through telescopes and then looking at stars and all the stuff. People think this is what we do. But honestly, I mean, I don't even know how many telescopes I have seen in my entire life as an astronomer, you know. I mean, and so many people haven't. So many people, I'm not kidding. Like, so many astronomers haven't even seen a telescope. Or they've seen it, but I mean, they have nothing to do with it. Because what we do most of the time, so in astronomy, we have people we call them observers, and then we have people who are theorists.
Yeah.
Right? So there are these observers are people who goes to the observatory and they run the observatory and they take data and all the stuff, right? And even that, these observers are not peering through telescopes. The telescopes are there and they are just observing. You don't have to stand there, and they're just recording this, and then you just take your data and then analyze it and make sense out of it and make beautiful images out of it. And then
you point the computer at where you want to look at and you get the data out of that.
Exactly. And then, so all these things, even you don't literally even have to be at the observatory. I can be here, and if I have access to a telescope, I just stare the telescope from the screen of my computer, and then the telescope is doing, just program something, just write a software and say, give it some coordinates and say, okay, I want you to look at this part of the moon, or, you know, just... So basically, so most of the time, astronomers are not at the observatory. We are sitting behind computers. This is literally what we do. We are sitting behind computers literally every day programming. Because even as an observer, you get your data, right? And the data you get is just binaries, zeros and ones. So you have to convert this binaries into like a human readable format. And how do you do this? You program. So you write a code and then you interpret, takes your data and make all these wonderful pictures you see of galaxies. Those are not drawings. Those are actual programming. These are things that have been programmed and processed to get those fancy images. And then there's another group of astronomers who are more like the theorists or the theorists. So basically what they are doing is they are developing models and making theories, like the name suggests, making theories and verifying theories and all this stuff. So they make all these models, and by making models, they're actually making simulations. Okay, so we believe that stars are formed by this and this and that and that and that. So they put this they code these things, write a lot of simulations and see what the star should look like after 10 million years. And then they confront that with observation. So this is what a typical day of an astronomer do, sit by the computer. The observer is analyzing his observation data. And then the theorist guy is writing simulation codes and doing the hardcore mathematics and writing simulation code. So for me, I'm doing both of this actually. So I need to, part of my PhD has to do with observation, and part of it has to do with, building simulations to actually, building simulations. So I'm on the threshold of both of these too. So my typical day is just sitting by the computer and I'm programming all day long. Just like any astronomer. So you see us at conferences and meetings, and we are showing these fancy pictures and we make it look so glorious, and it's like, oh, behind closed doors, man, it's not it's a lot of work.
Is that what you also thought when you went to conferences at your university back in Ghana?
Yeah,
it was so beautiful with the Hubble telescope.
Yeah.
Pictures. Which, if you don't know what they look like, you should just Google Hubble telescope. You get the glorious
pictures,
beautiful, colorful nebula pictures. Of the Horsehead Nebula and stuff, like in beautiful colors and yellow and green and purple and whatever. And then you finally got there. You finally got to do it yourself, and you thought to yourself, "Oh, computer."
Yeah, it's like people think, I don't know. It's like you take your picture, your phone. You know how you take your phone and you take a picture or something. Boom, Then you have like a whole picture. You can just print it on a paper. No. This is nothing like. Imagine that all these observations are done in radio frequency bands and infrared frequency and all these frequency bands. And when you see this, it doesn't make any sense to the optical eyes, And so then you have to take these numbers and convert into these beautiful pictures. And some of these pictures you see on one figure, it probably took the guy 6 months or even a year to get that picture out, It's crazy. Yeah. So this is basically what we do. Just sit behind the computers and develop heavy algorithm and analysis codes, and basically, this is what we do. And then those who are more, if you are more in the starting stage of the experiment, then some people are also involved in building the detector, So physicists turn engineers. So, and this is the beauty of astrophysics. I don't know about other branches, but the beauty of astrophysics is that everything we are doing is novel. It's not like I have a product, I can just go to the supermarket or the electronics shop and buy a telescope. No. These guys have not even thought about this stuff. The engineers haven't even thought about this stuff. So, because they don't need this, it's not something they think about on daily basis. Astronomers have a problem. They're like, oh, we need this and we need this specification and that and that and that and that. You don't go to buy this on the shelf. You have to build this. So you have to you have to turn to an engineer. You have to turn to a software engineer, because then you build this electronics. Now, this is just a piece of metal, wires and stuff. You need software. This software are not customized software that you just go to, I don't know, Microsoft or what, or Google Play Store and download. No. You have to hire some programmers from Poland or somewhere or someone to come and astronomers to come and do this for you, So and this is what makes the field really interesting, that at the end of the day, you have enough, because it takes knowledge from literally everything. It is, I mean, sometimes I can't even imagine what I have to do. Like, I have to know and I have to learn every day, like I never thought of that, becoming an astronomer, because then you have to become a software developer. You have to become what? Everything. You have to become a mathematician. You have to become a chemist. You have to become, it takes like everything from everything, You have to become a signal processing engineer. This is a whole field, but you have to just know this to just do part of your work. This is a whole field. Someone's career is built about signal processing, but this is just something something that's just a bit of your work, and you have to know this stuff. So, even though I think it's exciting. So at the end of the day, as an astronomer, you have this skill that makes you like, you can fit into many sectors. This is why you ask me, what do I want to do? I think I have options. I can go and work in a software company, or I don't know. Yeah, work even in the bank.
Basically anything which is mathematics related.
Mathematics, computers, then you are fine, like coupled with the fact that, okay, this common in every study is this critical thinking thing, yeah. But
yeah. Good. Actually, all right. One thing. I was reading through the website of the department, by the way, and one thing I was wondering about. Well, where in the VUB do you guys work? What building?
Where do they work?
Where do you guys in the VUB campus? Where are you stationed? Where do you work?
Yeah. So we are on the G building.
The G building. Oh, okay.
Yeah. So the astronomy department is on the 9th floor.
Mm-hmm.
Yeah. But
okay, because
yeah.
But because go on.
Yeah, but the 9th floor is the astrophysics department. But my group, which is the cosmic ray group, or astroparticle group, we are on the ground floor of the G building.
G building.
Yeah. So when you come to the ground floor, the G building, the main kitchen, our office is right by the kitchen. You can miss it. You can miss it.
So you got the good one, basically.
You can miss it, yeah.
Because actually, I read through the website of the A&A department as well, as well as all the other departments, and some interesting thing I found. I found many interesting things, but one of them I found is that apparently there is a permanent exhibition. Have you come across that one? I
haven't come across that myself, actually. I think it's something that was going on before I got here, but since I came, they haven't done this. Not to the best. So I saw this in the questionnaire. I called one of my colleagues who happens to be here 3 years now, and she also doesn't seem to know much about it. So I don't know. Maybe we are not aware.
Or perhaps they had it at some point and then they took it away, and then they never thought, they just forgot to take it off the.
Yeah, maybe. I don't know, because it was something I saw it too. I actually Googled because it was in Dutch, so I actually translated it to English, and I'm like, okay. Then I called my colleague.
I also thought to myself, never came across that one before.
Yeah,
I've never heard anything about this.
Yeah. So I don't know. Maybe it's still ongoing, but I don't know. Maybe it's something I need to find out. Yeah.
I'll ask around as well.
I will ask around. I can let you know. Ask my boss. My boss is the head of the department, so I can ask him.
Sure. And so something else I found as well on the website. It's the test your astronomical knowledge test.
Yes.
Did you ever do it?
No, I never. No, I actually never even go to that website. Actually,
it's in English. By the way, it's in English, but it's like 10 questions or something about the orbit of the sun and stuff.
Yeah.
I actually managed to get 46%, which as a I have to say though, as a non-astronomer, I'm quite happy with that.
No, but trust me,
I have to say also I guessed at guessed also,
Yeah.
But still, I was quite happy with that. But
don't be discouraged, because I'm sure even some astronomers, when they give them this question, they will still have a hard time because the interesting thing about astronomy is that the field is so broad that everybody is just focused on a very narrow end, it's difficult to say. So maybe sometimes I'm an astronomer and I go to places and someone asks me, talking about Big Bang and all the stuff, cosmology. Of course, I've done a course in cosmology. I mean, I know the thing, but I am not into this field. So when you ask me all these detailed questions, it's gonna be like
you can't go so deep into
it, exactly,
because essentially astronomy and astrophysics, it's but everything.
Yeah, it's about everything. It's everything.
The source of everything.
Everything. So it makes sense that everybody focus on a very small part, so we could build knowledge, about the whole universe.
Yeah, everybody does their own little thing, and the purpose of everything, and hope you get to something which is meaningful. Yeah.
Yeah, I mean, sometimes you even work with people in the same office, and you have no freaking clue what they are working on. Like. Give a 1 hour talk and you only understand like 5 minutes of the talk, like.
God, I would love to hear the conversations you people have in that cafeteria.
Yeah,
it just sounds like it could be interesting. It could be really interesting.
Oh yeah, people working on really outrageous ideas, and you're like, yeah. So one of the questions is like, how do people get information about new discoveries or?
Yes, yeah.
So I mean, for me, what I do is that there's this apart from friends, I mean, because I'm in the field, so you always hear, oh, there's this paper or this guy found this and stuff. So, but aside that, I always use archive. There is this archive for astrophysics. So every new paper that is being published is dumped there. So basically what I do is that every morning when I go to the office, I open archive and see there are different branches of astrophysics. So you go, okay, about galaxy, okay, cosmic ray physics, that, then you see all the, you just read, you can't read everything. So you just read all the topics and you read, okay, oh, somebody has found this. If this is interesting, then you read. So, I mean, this is how I get my information. And I think, it's a very easy and free way of getting, like astrophysics information is to go on archive.
Mm-hmm. And okay, in this archive, is it like a VUB archive?
No, it's open source. It's like
open source. Okay.
The whole world. So it's spelled as ARXIV.
ARXIV.
Yeah.
Right. Look at that.
It's for every field. So I think there's math, there's computer science, there's business archive. So you go there, you go for astrophysics, and then.
Let's say last question. What if somebody wants to get into this field? What do they need to know? What do they need to do? What is their course that they need to take? What do you advise?
I mean, I advise people to start early. So probably start at the bachelor level or something. Because if you get in like I get in, then it's really, really hard, because then you miss a lot of the exciting fun in the bachelor studies, which I have to do at some point. I mean, I did. I had to spend more time studying than my colleagues. So I think for astronomy, I think the main pillars you should focus on is about cosmology. Because cosmology just sets the whole foundation for everything. And then about stellar evolution, to talk about stars. So cosmology, and study more about stellar evolution. And general relativity.
Right, yes.
Yeah, so these 3 courses, if you have these 3 courses, you're good to go.
Because these are basically, these are the 3 pillars behind.
The 3 pillars, if you have these courses, same as particle physics. If you have these 3, because particle physics is also the same thing. It's just we are all looking at the same thing, but we are looking at the cosmological scale, and they are looking at the microscopic level. So these 3 courses, you're good to go: general relativity, cosmology, and something about stellar evolution.
So, that was Godwin Krampah, PhD researcher at the Astrophysics and Astronomy Department of the VUB. I thought that was pretty fascinating, don't you? We've learned a lot today about some of the big questions in physics, and also what the scientific community is doing to try and answer them. For instance, did you know that there was Project Ice Cube on the South Pole? Or that the moon is being used to detect exotic particles? Well, now you do. And we wish him luck, Godwin Krampah, in his hunt for exotic particles, which is a small prey but with huge rewards if he catches one. And who knows, before you know it, we'll see his face in the news when he's made his discovery that will rock the scientific world. Now that you've listened to all of this, I also want to know what you think. To begin with, why should countries invest in space exploration and astrophysical research when there is still such a mess back on Earth? Let me know what you think in the comment box. Thank you for listening to the Digital Republic today. I hope you found it as interesting to listen to as we found it interesting to make. This interview and other interviews, episode of the podcast and more are also available on my websites www.eschremer.com as well as www.democ.nl, and of course you can also find them on my YouTube channel. If you want to discover more about this subject, check out the extra information of this podcast or visit the website of the VUB's Astrophysics and Astronomy Department. I'll paste the link below in the comment box. And if you personally believe that the government should invest in the science of space and space exploration, then go to www.democ.nl and help us transform the Netherlands into a spacefaring nation. Now, what shall we talk about in the next episode? I really don't have any idea yet. There are just so many topics to choose from. Where to start? Well, perhaps we should talk about the value of democracy in times of political turmoil, such as the one we're currently living in, and why that right to choose your country's official leader is something to fight for. After all, this podcast is called The Digital Republic.